In this video, we're going to further study some properties of invertible matrices. To begin with, let's take a look at proposition 3.1.7, which has several properties of invertible matrices. To start out with, we have the fact that an n by n matrix A is invertible if and only if A is row equivalent to the identity matrix. So we've seen this in previous videos several times, but worth reiterating here. Next, if A is invertible, then the solution to AX equals B is given by X equals A inverse B. So sort of hidden in this particular point here is the fact that AX equals B has a unique solution, right? It says, specifically the solution to, right? So the solution to AX equals B, meaning that, there is a unique solution and we have the form of it using that inverse. Next one, we can find A inverse by finding the reduced or echelon form of A augmented with the identity matrix. Namely, if we take this matrix A and augment it with the identity, we can then row reduce it so that in place of A, we have the identity, and then where the identity once was is now A inverse. This was sort of our main technique we used for actually computing the inverse of a matrix. And actually, it sort of helps us along the way discover if a matrix is invertible, because, our goal there really is to try and row reduce A to the identity. And if we can't do that, then we know matrix A is not invertible. And then the last one here we haven't really looked at yet. That is, if A and B are two invertible n by n matrices, then their product AB is also invertible. And we have this formula that the inverse of that product, AB, so AB inverse, is equal to B inverse A inverse. So we sort of reverse the order of the of the multiplication there when we look at that product of the inverse of a product. It's not directly just the product of the inverses. Slightly unintuitive. I want to explore this a little bit further here because I think a lot of students might see this and say, hey, why are we switching the order? Why wouldn't it just stay the same? And so, the easiest way to see that this is the correct order is to, multiply AB by what we are claiming the inverse is, by this B inverse A inverse. And if that is truly the inverse of AB, then the result there should be the identity. That's just our definition of the inverse of a matrix. So if we take AB and multiply it by B inverse A inverse, okay, then, we can reassociate this multiplication. So we'd have A, and then I want to sort of put the B inverse together to highlight what's going on there. Okay, and then we know that the product of a matrix and its inverse is the identity. So this becomes A times the identity times A inverse. But the identity times any matrix is that matrix. So this just becomes A times A inverse, which equals the identity. And so since we got the identity when we multiplied AB by B inverse A inverse, that tells us that the inverse of AB, right, so AB inverse, must be B inverse A inverse. Notice that, I'll sort of show over here, if we take AB and multiply it by A inverse B inverse, we can't change the order of matrix multiplication. That's sort of one key fact that we looked at earlier with matrix multiplication. It is not commutative, and so we're sort of stuck here. We could reassociate still, right? You could say, A times BA inverse times B inverse, but we're kind of, there's nowhere to go here, sad face, right? So it really is important that we sort of switch the order of the multiplication when looking at the inverses. And of course, we could do this, the same sort of calculation that we did here by looking at the other way around. So B inverse A inverse times AB, okay, and this would, if we go through a very similar set of steps, reduce down to the identity, right? So we could see here, hopefully, some good reasoning for why when we look at the inverse of a product, not only do we know that the inverse of a product of invertible matrices exists because we can actually compute it here, but we have sort of the form of what it's going to look like. Next thing I want to look at is the inverse of specifically a 2 by 2 matrix. And so if we have A equals A, B, C, D, and then specifically AD minus BC, so we sort of, take the product of these diagonal terms, so AD, and then subtract BC. If that is not equal to 0, then A inverse exists. A would be invertible, and it equals this form here, 1 over AD minus BC times the matrix D, negative B, negative C, A. And hopefully with this formula, we see the importance of that AD minus BC term not being 0, since we are advised here to divide by that term. If it were equal to 0, we would be in some trouble there. This AD minus BC thing for a 2 by 2 matrix is what is called the determinant of that 2 by 2 matrix A. We will study this concept of the determinant further in section 3.4. There are generalizations of this to any n by n matrix, but for a 2 by 2 matrix, it does equal AD minus BC. And how can we show that this 2 by 2 matrix ABCD has that form for the inverse? Well, we can multiply them together and show that we get the identity, right? So let's go through that. So A, B, C, D times 1 over AD minus BC times the matrix D, negative B, negative C, A. Okay. And this 1 over AD minus BC is a scalar multiple. So we can actually sort of move that out front of this whole matrix multiplication. So maybe I'll rewrite that. So let's put the AD minus BC out front, and then we can, just look at those matrices multiplied together. So we'll put this 1 over AD minus BC, and then let's, sort of just directly multiply those 2 by 2 matrices, and then we can scale them by that 1 over AD minus BC, and hopefully we'll see the result is exactly the identity matrix. Okay, so we'll have our D minus B minus C A. Okay, and so we'll have that 1 over AD minus BC still out front times, okay, so AD minus BC right here. This is going to be a minus AB and a plus AB, so that's 0. And then in the next position, we'll have a DC and a minus DC, so that's a 0. And then in the last spot, we'll have a minus BC plus AD, or said otherwise, AD minus BC. Okay, and now when we scale by 1 over AD minus BC, we do in fact get the identity matrix. And this will work if you multiplied the other way around as well. So a good check, a proof, if you will, that this form does indeed give us the inverse of a 2 by 2 matrix. If we wanted to sort of see that in action, let's just do a quick example. So let's say A was the 2 by 2 matrix, 1, 3, 2, 4. First, a quick check. AD minus BC is 4 minus 6. So that is not 0, so that's good. So 1 over that, 1 over 4 minus 6 would be 1 over negative 2. And then, we can just follow that rule, the D minus B minus CA. So we're going to sort of switch the A and the D, and then stick negatives onto the B and the C. And if you want, you can scale those to just get sort of one matrix without the scaling. So we'd have a negative 2, a 3 halves, a 1, and a negative 1 half. So potentially a little bit quicker for 2 by 2 matrices than sort of going through the whole row reduction. But besides maybe being a little bit faster for actually doing the computation, a big takeaway for this formula is this kind of, 1 over AD minus BC thing, right? So giving us a little bit of insight as to why that particular quantity, that AD minus BC, not equaling 0, is really important in deciding whether or not our matrix is invertible. And will also give us some insight when we move into section 3.4 and explore determinants a little bit more. Next one we're going to look at here is the inverse of an inverse. So if A is invertible, then the inverse of A is also invertible, and the inverse of A inverse is just A. And this one's not too hard to show. So if we wanted to prove this, we want to prove that A inverse inverse is A. So we'd have to multiply A inverse by what we're claiming its inverse is, which is A. And we sort of immediately see that we get the identity. If we did it in the other direction, the inverse, our claimed inverse of A inverse, which is claimed to be A, if we multiply that by A inverse, again, we get the identity. So that's enough for us to see that the inverse of A inverse is just A. Maybe not too surprising, but nice to see that we can kind of prove that pretty quickly. So those are just some properties of the inverse. Okay, some of them are useful in proving other properties. Some are potentially going to come up as we work our way through different examples involving the inverse, but all of them, kind of good to have sort of in our toolkit here as we're working with matrices.